Today, we're going to do distribution of the sample proportion. And this is very much like the sample mean. And this is what we did for confidence intervals. We have a sample mean from a sample of size n. It has a standard deviation. And the standard error is the standard deviation divided by the square root of the sample size. And then from there, everything is how many standard errors out is the interval. So if this is 95%, we have a 95% confidence interval. This is what we did before. All right, so we're going to do it all over again, except this time it's for a population proportion. And this is actually very common. You see this on the news all the time. And a proportion is just yes or no. How many people are in favor? How many people are against? What proportion of people fall into that category? And you see this all the time with political polls. You see it on the news all the time. 50% prefer this, 55%, or 43% to 52%, something like that. So that this is one of the more common things that people encounter. If you aren't doing actual estimation for a population, this is what you'll see more often than anything else. And all this is out of n people. How many said yes? How many said no? So the p, the proportion, the sample proportion, is the number of yeses divided by the total number of people. All of this is exactly the same as the sample mean. The standard deviation is the same. But because it's a 1 and 0, it's an either or, it simplifies tremendously. Find an Excel, get an Excel sheet. We just need a blank workbook, any place, and I'm going to put sequence numbers down here so I can keep track of how many I've got. I'm going to number 1 through 20. And I'm using the fill command. You can do it 1, 2, 3, 4, 5, and so on. So here I've got 20 numbers. This is going to be my sample size. Once you've got that, put in 8 ones. 1, 1, 1, 1, 1, 1, down to 8. And then the rest are zeros. And this is a proportion. This is like asking people, do you watch the Westminster Dog Show? If you go to the bottom of this and do the average, and we've got an automatic command we can use. The average is 0.4 because we have 8 out of 20, which is 40%. If we did 8 divided by 20, we'd get 0.4. So that having a 0 and 1 makes every calculation easier. It doesn't change the basic formulas. They're exactly the same, except what you see is different. Here, do the stdev.p. And it doesn't need to be there. It can be anywhere. And this is the population standard deviation. The divisor is n instead of n minus 1. And there is the standard deviation for 8 out of 20. The formula that's used to get that. No, this is an improvement with age. The formula is p times 1 minus p. Take the square root. 0.4 times 0.6, 1 minus p. You remember the binomial? This actually is the binomial distribution. So that all the normal stuff we've got from other things is over here. When we used standard deviation, it was stdev.s for a sample standard deviation. That's normal distribution based. This is binomial distribution. So that it doesn't have a n minus 1 degrees of freedom thing. This always uses pure normal, standard normal z-scores. So instead of looking up some weird t value, you just look up a z value. And it's because this is binomial and not normal. So this, if you do the square root of 0.24, equals SQRT of 0.4 times 0.6. This is the square root of p times 1 minus p. And it is exactly the same as the variance or the standard deviation we calculated with the regular formula. Right, so everything is the same except for this dot p business. And all the rest of this shorthand version, is because we have ones and zeros, not numbers. They can be 2, 6, 7, 9, 55, whatever. So it's ones and zeros makes all of these formulas collapse back to a binomial distribution. And this, in fact, is the standard deviation for a binomial distribution. And it's easy to calculate. Also, and this is purely a practical matter, if you take everything from a p equals 0.3 up to a 0.7 and do p 1 minus p, like 0.3 times 0.7, take the square root. All of these things are going to come up to be about 0.5. This one was 0.498, and it was 0.4 and 0.6. In these things, if you ever have to do them, don't bother to calculate the standard deviation. It's about 0.5. So if you need a standard deviation and you don't have anything else, use 0.5. This is pure shorthand. I use it all the time because it isn't going to change. If you did 0.3 and 0.7, do that. Square root of 0.3 times 0.7. What do you get? Just like the 0.4, 0.6 we did here. This would be 0.3 and 0.7. About 458, about 0.46 to 2 decimal places, which is almost 0.5. So if you used 0.5 instead of using anything else, you aren't going to be very far wrong. And it's because the binomial has an end here and an end there. The normal goes from minus infinity to plus infinity. All of that probability is in there. Binomial, it's 0 up to 1. So it's got a hard stop on both ends. And this actually causes a problem when you get to small proportions, because it's like you're pushing to the end. You ever have a half deflated basketball and you push on it, and when you first push on it, it just goes. Then when you get down a little ways and start pushing harder and harder, it gets real stiff there. This is like taking the binomial and forcing it down to 0 or up to 1, and it gets like a hump there. So it goes along and then bang, it's got an end to it. It's like you drove into a wall. And that affects everything that goes on with this thing, because I can't get out of 0 to 1. The standard error of the mean for a proportion. And it is exactly the same as before. It's the standard deviation divided by the square root of the sample size. So a confidence interval is the proportion, the estimated proportion. I'm going to put a hat on it. This means estimated proportion. Anything with a hat is an estimate. I have an average, which is the p. This is just like the x bar, calculated the same way. And I have a standard error of the mean, which is s over the square root of n, this p, 1 minus p, square root divided by the square root of n. And I want to know how many standard errors out I go. Remember the empirical rule. Between 2 and minus 2 is 95%. Between 1 and minus 1 is 68%. So everything with the p uses standard normal distribution. This is actually minus 1.96 and plus 1.96. If I have 0.6 here, the standard deviation is 0.49. It was 0.4899. And I divide it by the square root of 20, which was the sample size I had. 0.49 divided by the square root of 20 about 0.11. So a 95% confidence interval for a population proportion, if the sample average, it's 0.4. Everything else is the same except it's 0.4. So this confidence interval is on the low end, minus 2 times 0.11. minus 0.22, and on the upper end, it's plus 0.22. That's two standard errors, up and down. This is a 95% bet. And it's purely standard normal distribution, although it isn't, so that this interval goes from 0.4 minus 0.22 to 0.4 plus 0.22. 0.1, 0.4, 0.2, 0.18 to 0.62. So my 95% bet on the real population proportion is between 0.18 and 0.62. What happens here is that if I have a low proportion, like a 0.1, the low end of this confidence interval goes outside the range of possibility. It goes below 0. Or if I get a 0.95 or something on the upper end of the confidence interval goes above 1. So I've got something that can't happen that I've calculated very carefully. In all of this stuff, when I had an average plus and minus a t-value times the standard error, this is called the margin of error. And it is, the t-value is n minus 1 degrees of freedom, the sample size minus 1, with the probability that you need. For a proportion, it's plus and minus the z-value times the standard error. And this is still the margin of error. In the X bar version, estimating a mean, we can have a percent error, which is the margin of error divided by the mean as a percent. This one, you don't do that. This is the percent margin of error that's quoted. So it's purely a width that you've got. Okay, the easiest way to do these is to do them. So we've got, we need MyOpen Math. We want to look at (3.2) estimates and confidence intervals. If I go to 3.1, don't go to 3.1. All of these are find the standard deviation, divide by the square root of n. That's all that's required in all of this. Statistics is really very easy because there's nothing there. So all of these are, like this one, you've got a population with a standard deviation of 51.2. The mean of the distribution of sample means is that mean, and this, the standard error, is 51.2 divided by the square root of the sample size. So this square root of the sample size divisor, this thing, is always the same, no matter what you're doing. And anytime you see find the standard error, take the standard deviation divided by the square root of the sample size. Don't even think about it. Okay, back to the one that's got things that are important. This is where the proportions and the averages go different directions. For a confidence interval for a mean, an X bar, I have to use the t value. So that for this one, for example, sample size is 28. How many degrees of freedom? No imagination. How many degrees of freedom for n equals 28? 27. Subtract 1. Always. If we go into Excel, and I need a 94% confidence interval, and this is the same for all of this stuff. I need a 94% confidence interval. What do I look up in the t.inv? Confidence interval is always in the middle. How much is outside of 94%? 6%. Subtract it from 100%. How much is in this tail? 3%. And 3% here. So what do I need to look up in the t.inv? Let's get the Excel, and it will tell you what it wants. Equals t.inv. It wants a probability and a degrees of freedom. The probability, I've got two choices. What are my choices? Here's my confidence interval. These areas always come from the left. I can look up 0.03, which would be this one, or 0.97, which is the 0.03 plus the 0.94. The table and the computer always gives you the area from the left. What's the difference if I put in 0.03 or 0.97? Positive and negative. They are symmetric, so one end is just like the other. So I have 0.03 with 27 degrees of freedom. And that is 1.9 minus 1.963. Suppose instead of a mean, we were looking for a proportion. I want a 94% interval on the proportion. I don't use the t. I have to use the norm.s.inv. So if I go to here, equals norm.s.inv, standard normal probability, I put in exactly the same probabilities as before. I can use 0.03 or 0.97. This doesn't change in the least. If I put in 0.03, I'm going to get the standard normal distribution, which is minus 1.88 on one end, plus 1.88 on the other. That's the number of standard errors up and down I have to go. The t has sample size involved. The normal doesn't. This is for sampling means, the 1.96. The 1.88 is for proportions, because it is not a normal distribution, really. So there's only a few moving parts in these things, and they are basically all the same. Here, for a confidence level of 92% for a mean, that means I got a sample size, I got a t-distribution. What values do I look up for a 92% confidence interval? The confidence interval is always in the middle. What's on the outside? 0.8. How much in each end? So I can look up 0.04 or 0.96, because I come from 0.4 up to 0.4 and then go 0.92 further on. And this is the plus version, that's the minus version. This is, number 3 is for a proportion. It uses a z-score, the norm.s.inv. 85%. What am I going to look up? 0.85 in the middle. What's outside? 0.15. What's in 1/2 of the ends? 0.075 or 0.075 plus 0.85. Five, 12, 0.825, 0.075 or 0.825, and it is norm.s.inv. .075 1.44 negative, or what was it, 0.875? 0.825. Is that right? That can't be right. That's less than 0.85. What is it really? 0.925. 0.075 up to that plus the 0.85, 92.5%. So it's equals norm dot S. It's not going to like that. Norm dot S dot INV 0.925 and all I do is get the positive version of that. So for the confidence interval for a proportion that is 85%, I multiply 1.44 times the standard error of the mean. That's my margin of error. That up, that down gives me the 85% confidence interval. The confidence interval lower limit and upper limit for a population mean. And it's the same for a population proportion, are 19.6 to 24.2. That's the lower and the upper end. What is the sample mean? Confidence interval, the average plus the margin of error minus the margin of error. What's the sample mean? I got two ends. I go up and down the same amount. What's the sample mean? Where's the sample mean? In the middle. All I need to do is find the middle of the confidence interval. This is important when you're reconstructing something, which is usually more difficult than making it in the first place. But this, 19.6 to 24.2, if I average those, 19.6, and I can just put them in there, 24.2 plus 2 divide. The middle of the interval is 21.9. The sample mean is 21.9. It's what's in the middle of the confidence interval. When you see a confidence interval, the middle is the average or the proportion. I'm going up a certain amount and down a certain amount, and that certain amount is called the margin of error. So what is the margin of error here? How far up from 21.9 and how far down from 21.9? 21.9 minus 19.6.
2.3, Bob.
2.3. What is 24.2 minus 21.9? 2.3 as well. It's 21.9 plus 2.3 and minus 2.3. If I have the ends, I can reconstruct the middle. And if I have the sample size, I can go all the way back to the standard deviation. This is another one. 59 to 62.8. What's in the middle? What's the average? And what's the margin of error? What's in the middle of 59 and 62.8? 60.9. Average 59 and 62.8. Add them, divide by 2. The middle is 60.9. What is the margin of error? 60.9 down to 59 and up to 62.8. Subtract 59 from that. 1.9. 1.9 up, 1.9 down. Here is a proportion version of the question. The interval is 0.26 to 0.46. What's the proportion from the sample? Average them. What do you get? 0.46, 0.26, 0.72, 12.172, half of that, 0.36. Is that right? 3.7. Okay. 0.37. The margin of error then is whatever the middle is minus the lower end or the upper end minus the middle. I'm going the same distance up and down. No, it's 3.6, not 3.7. That's 0.72. Divided by 2 is 0.36. And it's 0.1 up and down. What is the sample size? I got 0.36 and a margin of error of 0.1. 0.36 plus and minus 0.1. What's the standard deviation? This is why proportions are so easy to deal with. Square root of p, 1 minus p, 0.36 times 1 minus that, 0.64, hopefully, 0.54. What is it? 1 minus 0.36. 1 minus 0.4 is 0.64. Square root, 0.36, 0.64. 0.36, 0.64 times square root 0.48. Z times the standard error, 0.48 divided by the square root of n is equal to 0.1. What do I need to solve this for the sample size? I need to know the z value. I need to know what percent confidence interval it is. What if it's a 95% confidence interval? Z is about 2 times 0.48. Square root of n is equal to 0.1. N is equal to 2 times 0.48 divided by 0.1 squared. Two times 0.1 divide, square it. It's about 93. Right? With the proportion and the formulas, you can reconstruct the entire thing.